Okay, so now continuing our read-through of this paper by Nelder and Wedderburn on generalized linear models. We are on section 2.1, the maximum likelihood equations. Just as a reminder, the link to this paper and the complete playlist that I'm making with videos on this paper will be in the description of this video. Okay, so reading through this first paragraph here, they're saying something about the maximum likelihood equations being equivalent to an iterative weighted least squares procedure. And then they continue to go on, and then there's a proof. So this is actually where I want to spend my time right now on this video. Let's just talk about this first part of the proof, equation 7. Okay, and they're saying that equation 7, it comes from equations 3 and 6. So when I go to my Blackboard, I've also written those equations down. And I will provide the link to the videos where we talk about those equations. We've talked about them previously in this playlist. Okay. Also, before I move to my Blackboard, I want to point out that this theta, I believe, is a typo. It should say phi. Okay. Alpha of phi, not alpha of theta. It is a typo that I would imagine that they later correct. And so, yeah. So let's go ahead and go to the Blackboard and show equation 7. All right. So observation Z come from the following density. Don't forget this is the exponential family distribution, and this is basically the layout of GLM. We have these observation Z from the exponential family distribution. We have Y, which is the sum of some unknown or parameters beta sub I times these independent variables xi, where the xi values are known and observed. They're independent variables. Note that these betas, these are unknown like regression parameters. It's nothing to do with this beta over here, which is this is a function of phi and z. It's kind of unfortunate that they chose the Greek letter beta, because that's not to be confused with the beta that you see here. Okay. And then we have theta equals f of y. This is our link function. It connects this systematic part to the random density. All right, equation 3 I've written here, and equation 6 I've written here. Again, the link to talk more about these equations will be provided in the description of this video. Okay, here is equation 7, and this is what we want to talk about right now. And this is what we want to show in more detail. Okay? So, just as a reminder, L is the log likelihood function. So the log of our density function for Z. Okay? Which would be the log of the exponential family, right? Oops, I wrote alpha theta. Alpha phi. Okay. And then, let's see, make sure my parentheses are all right. Okay, and then notice that the log and the exponent cancel each other. So it's basically just the stuff on the inside of, or in the exponent here. Okay. All right, so now I need to take so this is the likelihood function. So I need to take the derivative with respect to beta. To one of the betas. This first piece here, that is phi, right? Alpha of phi. Let me rewrite that. Okay. Phi does not contain beta. Okay. What do I mean by that? Well, let me go back up. Let's remember, what is beta? Beta is contained in y, right? Y is, in other words, y is a function of beta. Also, theta is a function of y. So if theta, let me write this here, Theta is a function of y. So theta is also a function of beta. Right? I could plug in for y. Okay? And I would see that theta is a function of beta. But phi is not a function of beta. Only theta is. All right, so alpha of phi is basically a constant, and when I take the derivative, it's just going to stay out front. All right, next, I'm going to take the derivative of z times theta with regards to beta. Okay, theta is a function of beta, so I have to take the derivative with regards to beta. Then I need to take the derivative of g with regards to beta. Okay? Then I need to take the derivative of h of z with regards to beta, but z is not a function of beta. So it's basically taking the derivative of a constant with regards to beta, which will just be 0. So basically it gets dropped. Same thing out here. Remember, this is a function. This beta is not a parameter. So this function of phi and z, where phi and z, neither of them are functions of beta. Neither of them are functions of our regression parameter beta. So therefore, when I take the derivative of this with regards to beta, it's 0. It cancels out and it goes away. Okay? All right. So now I'm going to use the chain rule, and I'm going to write this as derivative of z times theta with regards to theta times derivative of theta regards to beta. Okay, so this is the chain rule. Okay, minus, and I'm going to do the same thing here. Okay, and this is convenient for me to do this because now things simplify a little bit. So what do I have here? The derivative of z times theta with regards to theta, basically z, so it's the derivative of z times theta with regards to theta. So basically z, it's just going to be the constant z, right? Because the derivative of theta will just be 1. So the constant z will stay out front. All right, I'll leave this here for right now. I'll come back to that. And then derivative of g with regards to theta. G is a function of theta. Let me see. Did I write this down somewhere earlier? This is by definition mu, which I'd have to go back, but I think that is let me actually go to the paper really quick. Where did we see that? Here it is. So the derivative of g with regards to theta, right? That's what that's prime notation. So it's directly before equation 3. Okay? You see that that's how they've defined mu. Okay? So this here is mu by definition, and we discussed it previously. Okay, and I'll provide again the link to that video where we discuss that in more detail in the description of this video. Okay. All right, notice I have this guy showing up twice. So what I'm going to do is pull it out of my parentheses. Okay, so I have z minus mu d theta d beta I. Okay. Okay, we see I'm getting closer to what you have here, but not quite. All right, so let's keep going. All right, let's break this up. D theta. Theta is a function of y. Remember, theta equals f of y. That's our link function. So I can write this dy times dy d beta sub I. Okay. Now remember, y equals the sum from I equals 1 to m of beta I xi. So if I were to take the derivative of y with regards to beta I, okay, I'd be left with all the other betas times x, so like, say this is beta 1, right? Then when you do the sum, beta 2, 3, 4, they'll all be dropped when you take the derivative. So all I'll be left with is that beta 1 times xi, right? And I'm taking the derivative of that with regards to beta I. So basically I'll just be left with whatever the corresponding xi is. Okay. You might want to write out this sum. If that does not make sense right away, you can write out that sum, and then you can show this, that this derivative is just xi, whatever the corresponding I is. Okay, so let's go ahead and write that. Let me scroll down a little bit. D theta dy times xi. All right. Let's see. One more thing I could do. I'm trying to get it to look like this. Although I guess I never directly used equation 3. Maybe I could have, and then I would have gotten here quicker. But I definitely want to use equation 6 to help me get here, because I do see this v showing up, and what I have currently doesn't have v yet. So I see d mu d theta. So let me go ahead and do chain rule one more time. Okay. D theta d mu, and then d mu dy times xi. Okay. Now, if you're looking at this and you say, well, okay, well, v equals, by equation 6, right, it was d mu d, or I should be using partial derivative, d mu d theta, right? And this is basically the inverse, 1 over v. Due to properties of inverse derivatives, you can actually just invert this as well. Okay. So this is a property of inverse derivatives as long as v is invertible, which it is. What do we have? Z minus mu times 1 over v. Okay, by equation 6. Du dy times xi. Okay. So let me see here. Equation 7. Yeah, that's basically it, right? They just have it written a little bit differently. They have z minus mu, and then they just put y or v underneath. A little more compactly, but there you go. So we can see equation 7, that looks to be true, right? That makes sense how we got here.